So this is a session about working through coding kind of the workflow of machine learning. If you're here for the zoology class that's downstairs and around the corner. So let's get started. And I want to kind of set a baseline here a little bit. I want to get a sense of who here would say they've done some sort of machine learning in any context whatsoever. OK, great. Who uses it kind of in their day-to-day, either at work or on their nights and weekends in some form, in some fashion? OK, great. So that's an interesting kind of contrast there, right? And hopefully I can get more of your hands up in that second round after the session. OK, so just to get everybody on the same page, the context in which we talk about what machine learning is for the purposes of our next 40-ish minutes is programming with data. If this will click, OK. And what I mean by that is I want to drive the focus of a lot of the machine learning work on the data aspect of it, because that really determines how far we can get in our efforts to build intelligent systems. Is how good is the data? Is it reflective of the world around us? Is it reflective of reality? And does it keep track of the shifting realities as time passes? So this slide was put here on recommendation of someone else, that I show you what these 7 steps are before we get into it. Help give you guys some visual context. So we'll go through each of these in detail, so you don't have to memorize them right now. But the 7 steps, as I see it, for the purposes of our talk, is to start with gathering our data. But that's not enough. We need to take that data, and we've got to do a little processing to prepare it a little bit. And once we have that data ready, we need to choose and build some sort of model for that data. Once we construct said model, we can train the model and evaluate the model, because one without the other isn't quite enough. And then once we're done evaluating that model, there's still some more work to do before we can really deploy it. We need to play around with some of the parameters and tune it up a bit. And then we're ready to make some predictions, do something useful with our machine learning model. OK, so what is it that we're going to be doing today? Today we're going to make a model to try to categorize text from BBC News reports around 2004, 2005. This is a data set that comes to us from the BBC directly. And we'll take it, we'll kind of clean it up, structure it in a way that's suitable, and apply some machine learning to it. These are the 5 topics that we'll be using: tech, sport, business, politics, and entertainment. And so our model will take in some sort of, literally just like a string of text, right? And it needs to figure out how to, by some means, select one of the 5 categories. In this case, this is an example of an article of tech. There we go. The slides are slow today. OK, so let's get started with gathering our data. As I mentioned, our data set is coming from the BBC directly, but there are, of course, many ways to collect our data. And thinking about where your data lives in the context of the problem you're trying to solve is critical. Because sometimes you could afford to take your data months, maybe years in the past, right? You store it, you archive it, and then someday you come around and you say, you know, it'd be useful to do something with this data. But in other contexts, you may need to be doing machine learning or other analysis on your data live or almost live as it's coming in. And sometimes you don't even have the data yet that you want. So you need to build systems to keep track of this data as it's coming in. Perhaps add new fields to existing databases or other data storage mechanisms, and provide ways to store this data so it doesn't get lost in your logs or get lost just along the pipeline of processing that happens. There's a lot of places where data sets live that you can use to kind of learn and get started and experiment with. One example is BigQuery's public data sets. there's about 40 plus data sets of varying sizes. They all live in BigQuery, and they're all free to access. They're stored there, and you can take them, play with them with SQL, and then when you're happy with it, you can store it as a table, export it as a CSV, do any number of things. You can join each different tables together with your own data, et cetera, et cetera. In our case, the BBC data set comes to us from the BBC's website. There was actually a paper on it back in 2006 from the BBC, funnily enough. And there's about just 2,000 documents, right? 2,200 plus documents. It's not a huge data set, right? This is kind of our, I don't want to call it a toy data set because it is real data, but it's not huge, right? We're not dealing with huge data here. And that allows us to do things kind of more quickly for the purposes of this talk. So for some reason, the font has decided to be funny on me and overlap a little bit. Hopefully it kind of comes back down as we go along. But basically, this is kind of almost, we're now getting into the process, preparing of that data. But I stuck this still with the collection of it just because this is just taking that original raw data, which was actually these thousands of articles were each an individual text file. So they weren't quite ready to be used in the context of a CSV or any other kind of structured data format. So I've done a little bit to stick it into a table, then pull it back out and strip out the characters I don't want, make it all lowercase, things like that. And so that I just have two columns, the category and the body of the article. The title is also there. So it's the title and the body of the article just kind of smushed together. And so that brings us to our second step. Preparing our data means to take this blob of text, right? It's still not super cleaned up, and turning it into a format, into a structure that is suitable for running our model against. There's a bit of a catch-22 here, because you kind of have to know what model you're going to be preparing or creating in order to prepare data for that model, right? This is a point that often I find people get tripped up on. It's like, well, I don't know how to structure my data yet because I don't know what model I'm going to use. And unless I know some kind of, in some cases, core fundamental things about the structure of the model, there are some big changes that might have to happen to the structure of my data. Let me show you an example. Our data is not super structured, right? It's free-form text. Some of those articles are really, really long. Some of them not so long. We need a way to represent the articles in such a way that it's useful for machine learning. And specifically what I'm getting at is we need numbers, right? And not like the figures that are cited in these articles. But we need to turn this text at some point along the way, eventually, into numbers. Because at the end of the day, a lot of what's happening with machine learning is crunching numbers together with various matrix multiplies and et cetera. So here is one admittedly very simplistic way to think about text and structuring that text in such a way that it becomes numbers. So let's say we have a bunch of labels, right? We have our 5 labels, and we have a vocabulary, quote unquote. This is words that we know exist that we care about. So this is a extremely cut down version, right? Usually your vocabulary would number in the thousands, if not higher. And so here we have, what do I have, like 10, right? So these are 10 words, let's say, we care about in this mock example. And let's say there's an input, this sentence, gadgets on show at the 2005 Consumer Electronics Show. Those words are mapped to the vocabulary. And only the words that are in our vocabulary are we able to read, essentially. Those are the only words we care about. And so we say, well, gadgets and electronics, those are words in my vocabulary. And so I'm going to represent my vocabulary, instead of 10 words, as an array of length 10. And just start them off, initialize them all to zeros. And to signify which words are in the sentence for this input, I'm going to say, well, gadgets is in there. So I'm going to turn that, what is that, 1, 2, 3, 4, fifth word, right? Gadgets is the fifth word in our vocabulary. We're going to turn that into a 1. And electronics is the 6th, 7th, 8th word. So the 8th value in that array is also a 1. So in this way, we have turned this sentence into an array of numbers. And so now we can do the same for our labels. Those 5 values that we had originally, that we start. Click. OK. Those 5 values that we had initially, we can also arrange in the same manner. 5 words, array of length 5. And whichever one is the correct label for a given input, we'll turn that one to a 1. So in this case, it's the second value. So the second value becomes a 1. In practice, when a machine learning model makes a prediction, quote unquote, OK, I think my clicker is actually dead, unfortunately. OK, what actually comes back are a bunch of floating point numbers, decimals, which should, in the good world, add up to 1. And it's the biggest value that we care about. And so while in the ideal case, we have our values encoded as 0s and 1s, in practice, when they come out, they become decimals, and you pick the biggest one as what you consider to be the acceptable answer. So when it's the highest one here, and then a different value, for example, here, then it's the 1, 2, 3, 4th value. So we take the 4th value and put it there. And looking at this now, I realize I put 6 values in that array, so that's a typo. OK, so I promised code. So here's code. We're going to go to Colab. How many of you guys are familiar with Colab or Colaboratory? Awesome. So everybody else, you're about to get an amazing amazing tool dropped on you. Let's put it that way. So Colab is Google's hosted notebook. If you have a Gmail account, you can access Colab. It is free. You can access GPUs. You can share your notebook with others. You can edit in real time, add comments. It's basically Google Docs, but with Python, which is awesome, right? So, and you can upload, download the files, et cetera, et cetera. OK, so enough talking, more showing. So this is Colab. The notebook I'm running we'll just flip back and forth between code and slides going forward here as we go through each step. Those of you who are not super inclined with the code, hopefully you'll still be able to get something out of kind of these 7 steps and the conceptual walkthrough of the ideas behind what we're working on. So after all our imports, the data that we're going to read in comes, as I mentioned before, from BigQuery. So after I did that query, I did export it to a CSV file, and then I uploaded it to Google Cloud Storage. Colab has access to gsutil, which is like the Google Storage utility command line tool, but it's also hosted online as a public link, and pandas can read that link directly down. So it's like, oh, I can just shorten this down to 1 line. Fantastic. So our data looks exactly as we expect, right? It's rows with the category and the text in that body. And one thing I like to do is to check to see, are my 5 categories reasonably distributed? Is one of these categories only have 10 examples, for instance, right, which would make it somewhat less than useful? It's close enough. I mean, yes, there are some in the 500s and some in the 300s, but all things considered, could have been worse. And what I'm going to do now is split them up into training and test, right? So this is the data preparation part. And so we'll take our data and separate out. In this case, I chose 0.8. So 80% of our data will go to training data, and 20% that is left over we'll set aside. We'll set it aside and use that later to assess our model, use it to evaluate our model. And so this is kind of what I mean when I'm saying that you kind of have to go through the steps and then come back and do it again, because they reference each other in ways that are a bit of a catch-22. So stay with me here. OK, so let's see. I said we go to the code, and and we'll move on to choosing a model. Okay, so before we do that, let's talk a little bit about tokenization. All the things I said about taking the text and turning it into zeros and ones, right? Long arrays in this case, of zeros with a couple of ones in there, the ones that represent the words in our vocabulary. In code, it takes a little more than a slide or two. So the first thing we'll do is, in Keras, there's a pre-processing library, and one of them allows us to tokenize those words into those individual zeros and ones. So there's a nice max words argument, which accounts for how many words will be read in, and then we'll break them down, and then we want to fit them to the text that we have. So that's mapping the words to zeros and ones. And in this case, we're limiting it to 1,000. We could make that limit higher. We could make that limit lower, just to kind of see how it affects our system. And we'll do that down the road here. And then we said we wanted to transform our labels too, right? The labels also need to become zeros and ones. That's the 5 categories. So we'll take our labels here, what I call train cat and test cat. Cat is short for category, and we'll save them to our y values. So we've got x and we got y, so inputs, outputs. And then one final thing we need to do with our outputs is turn the actual values to zeros and ones. So this encoder.transform turns our text into 1, 2, 3, 4, 5. Like literally, like the 5th value is now the number 5. So now we need to change the number 5 to an array of length 5, where the 5th value is a 1 and everything else is a 0. So there's like a multi-step transformation here, for better or for worse. Thankfully, you don't have to really change anything. If take my code, and it'll just work against text at least, right? And in a lot of cases, your pre-processing will be simpler than this. Text can sometimes be extra kind of convoluted just because it's so free-form, right? You can literally write anything, right? It's just a string. And so getting it into a nice structured format that's suitable for doing something with can sometimes take a couple extra steps. But we can see here that looking at the shapes of our x and y, that we have 1,780 training examples and just under 450 test examples. And you'll notice that this 1,000 is present here. So that means we have 1,000 words in our vocabulary. So remember back to the slide earlier when we had, well, I can just show you. When we had those 10 words, right? That was the size of our vocabulary. Okay, so our vocabulary is now 1,000 words. And for each input sentence, right, these articles, whatever top 1,000 words basically were in that entire body of training data, we'll say only those count as inputs. So words that are less common maybe won't get represented, things like that. And so that's why you end up in situations where for any given sentence, some words are left out. And then for our training labels, for our labels, we have 5, our 5 values. So that's the length of that. Okay, so let's flip back to the slides and speed back up to where we were before. They should really have like a function to just like jump to the other slide that we were on. Okay, so choosing a model. We're playing with text today, but there's of course a wide world of machine learning models out there to choose from, right? How do you pick the best one? In my view, you want to just pick one that will do something. Start with perhaps the simplest thing, as we're doing here, and iterate from there, because a lot of the work, as we're already beginning to see, falls upon the data collection, the pre-processing, and all the instrumentation that needs to go around it. Swapping out the model oftentimes is just something you do that's just like, yes, it's at the middle of it all, but it's not that many lines, and it is oftentimes isolated from everything else. A lot of the modern day libraries for doing machine learning have smartly decoupled the choice of model from everything else, so that you take your data, you do a bunch of stuff, and then eventually it gets into some format. And that format is consistent across all the different models so that there's this interface, right? And that allows you to swap out the models without needing to worry about it causing your entire pipeline to break for preprocessing and so on and so forth. Now, this is specific to each data format. So if you decide to switch your data from text to pictures or from text to sound, things are going to break, right? But for any given class of data input, let's say you're working with sound files, the types of models, for the most part, that work with sound all kind of rely on the same principles in terms of their input structure. So once you figure out how do I get my data structured in the right way to work with sound, then you can play with various models and tune them and try more advanced things, but then your preprocessing is like basically done. So my clicker still doesn't work, and we're going to use the keyboard. OK, so who here has used TensorFlow? Who here has heard of TensorFlow? Cool. Welcome to DevFest. No. The session after me, Josh Gordon will be doing a kind of walkthrough of TensorFlow's high-level APIs in more detail. And so if you haven't had a chance to play a lot with TensorFlow, definitely want to stick around for that. It's here, same room, different time. And we'll I'll of course be showing you stuff, but I won't be going as in detail about like every line that we're going through. But I will talk a little bit about TensorFlow's kind of internals. Right? TensorFlow is written mainly in Python, but supports lots of other languages now as well. And it is running on top of a distributed execution engine. And what that's getting at is that it doesn't really care what hardware it's running on, whether it's your phone, whether it's a server, whether it's a GPU, whether it's your laptop. Your code, for the most part, remains the same. And on top of that kind of raw Python library that's what we call the core API, you have the layers library, so tf.layers. And in there kind of is also Keras, which is what I would argue is a simpler, perhaps more developer-friendly way of accessing kind of model building and execution. That's what we'll be looking at today. And for the, let's call it the trivia crowd, the brain trivia crowd, the estimator API sits parallel to Keras, but is like something that was developed independently, or at least it was part of TensorFlow before Keras was pulled into TensorFlow. History lesson here. And it is particularly useful when it comes to doing distributed training at the server level or doing kind of large machine learning jobs. So, model selection. One of the questions that I sometimes get is the notion of like, what is exactly happening when a model is fitting to data? Right? And usually I'll make some reference to the classic line plot where you draw a line of best fit through a bunch of data, but this animation looks better, so I put this here instead. This is a simple example of orange dots and blue dots, and you want to try to split the region, and it's training, quote unquote, and kind of figuring it itself out. And of course, you want to be able to see it working for more complex scenarios as well, where you have shapes that are perhaps not as easy to draw a dividing line between. OK, so building our model. We want our model to, in this case, it's not like a super, it's not a super advanced text model, right? But we'll see how it does. So we start out with saying that our model is sequential. It's a sequential model. And we're going to add one big layer to it. This is basically, we had 1,000 words in our vocabulary. Right? That means each time it comes in, the data comes in, it's loading in an array of length 1,000, literally. And so we want our model to be able to handle that. So it needs to be pretty wide to kind of take that input in. So I've chosen 512 because it's a nice factor of 2. But you can choose other large numbers as well, I suppose. And our input shape, right, this will be 1,000. And activation function, in this case, we'll choose ReLU, so it's a rectified linear unit. I'm going to leave that detail to Josh's talk after mine, and just say that it's part of kind of structure your model such that it will be nonlinear, so that it can train to nonlinear data. We have 5 different classes, and we want our data not to come out as a bunch of big numbers. We want to split it into a probability distribution, so it adds up to 1. And so that's what this activation function of softmax takes care of for us. It turns the inputs to this layer into a probability distribution, so it adds up to 1. And finally, we want to compile our model. What this means in Keras terms is we'll give it a loss or a measure of error. So it's saying, how do you want me to measure error? How do you want me to compare the outputs that the model is producing against the true answer, right? Our true answer in this case, maybe it was like 1, 0, 0. The output here is 0.95. So it's like close, right? And in some cases, it'll be really far off. And so that's a numerical measure because you have 2 arrays of numbers. You can pick an optimizer, and in this case, we care about accuracy as a metric. And so let's look at that in code real quick, and then we'll move on to the next step. All right, so training the model. This is literally the slide that we just went through, so no edits there. We have chosen to, oh, well, it's not literally. Sorry, I did add one thing. I added dropout. So one of the things that, I guess not in like super recent years, but that got developed as things went along, is adding a layer of dropout in your deep neural networks. And that allows models to, helps prevent overfitting. So it helps us prevent the situation where our model ends up memorizing the training data. And then when new test data shows up, it's like, I don't know what this is, because I memorized everything over here, and this doesn't look exactly like what my training data looked like. So we want to help it generalize a little bit. And so dropout basically says during training, it will randomly knock out certain nodes, certain ratio of these 512 nodes, but it'll change with each training loop. So as more data, as each kind of cycle or batch of data shows up, it will knock out randomly a different random selection of those nodes. Okay, so that's our model creation. Great. Training. Okay, so training in this context is pretty straightforward. We can just call .fit on our Keras model. Training takes our training data, pushes it into our model. It makes a prediction, right, ostensibly. And it looks at that prediction and compares it to the correct answer and uses that to update our model. And it does this over and over again until it either runs out of data or stops by whatever metric that we've given it. Okay, so evaluate looks the same as training, except we swap out the training data for evaluation data, and then we use that to just calculate the accuracy. Notice that we do not update the model when we do evaluation, right? Because it's like, that would be like if you took a final exam and you got to look at the answer key while you're taking the exam. Wouldn't really work. So in code, that looks like calling .evaluate and passing in essentially the same arguments. And so that looks as promised. We call .fit, and Keras will output a couple of different metrics. We have loss, or you can think of it as error, and accuracy. And then Keras does this nice thing called validation for us. So you see here there's a validation split. It takes the training data and splits it yet again. In this case, takes 10% of that and sets it aside and helps us give and doesn't show that during that training run, and helps us give a somewhat accurate read on, is the making sure the model doesn't overfit and kind of keep track of the accuracy that way before actually using the test data, which we'll use here when we call evaluate. And so in this case, we have a vocabulary of 1,000 words. We trained it over 2 passes of the full data set, and we got an accuracy of 93%. It's a pretty straightforward model. It's a pretty big model, 1,000 words for such a small body. There's only 2,000 articles and only 5 categories. So what we could do is, if we wanted to challenge it, we could reduce the vocabulary. Is one kind of interesting thing if you don't want to kind of be playing with those tenths of like, well, I got 93.6 instead of 93.7%. Is that just an error, or did something really happen here? So that's kind of where hyperparameter tuning comes in. In this case, we just have a few kind of straightforward models. I wrote a bunch of stuff here because I'll give you this notebook so you can read that. But basically, hyperparameter tuning involves taking your model, training it just like you did before, but then making a variant of that model, changing some parameter. Right? So this is the parameters of the model, not the things that we're training, but things like how much data do we show it on each pass? How many times do we pass through the entire data? We talked about dropout earlier. So what is that dropout ratio? Is it half? Is it a third? Is it a quarter? How many, what else was there? Batch size, epochs. Oh yeah, you can also pick things like the optimizer, the way we measure loss, things like that can also have a play into it. With regard to the optimizer, there's also this notion of a learning rate, which is how fast, how big of a step does the machine learning model take as it's trying to train. And so hyperparameter tuning involves playing around with these numbers, this data, and figuring out which works best for my particular model paired with my particular data set. Now, you could do something like I've done here before and taken all the code, drop it into a function that is parameterized with a bunch of the things that we're trying to play around with, and just literally change these values and rerun this function and take a notebook and start scribbling down the accuracies. Right? Hopefully, you'll do this once and then realize, I think I can do better. And maybe you do something more sophisticated and decide to nest 3 for loops together and try to see if in this case 27 different runs of the model, which one works better here. And if you decide to be more advanced than that, you can explore things like there's various kind of search algorithms for searching through this parameter space, including, you guessed it, machine learning models for doing it. So, meta. Okay, so let's say we did all this hyperparameter tuning and we trained our model and we're happy with it. We want to deploy it. We want to make some predictions. In Keras, it's pretty straightforward. We show the data, we call predict, we get the value we want. In this case, it looks something like this. We want to do model.predict, and we pass in the values of that sentence. And here's just a couple of sample ones, I don't know, for sport. And let's see. And that's our 7 steps of machine learning. So I think because we started late, I'm technically over time. So I will move quickly through the final little tiny portion of the presentation here. How many people have heard of Kaggle? Oh, fantastic. Everyone else? You saw who raised their hands, right? You can ask them about how awesome Kaggle is. Kaggle is a data science platform. There's competitions, there's a lot of discussion, there's a lot of data sets, and there's also a hosted notebook that you can run for free and has GPUs, et cetera, et cetera. So really neat, kind of different use cases, right? With Colab, it's really useful for you want to run a notebook, and it's very focused on having a great notebook experience. Kaggle is a little more broad-ranging. It's a community. There's forums. There's data sets, and so on and so forth. So they're kind of different things, but at the same time, they both support upload and download of your notebook files. So they're pretty interchangeable. I mentioned that we can do better with the hyperparameter search than doing a triple nested or perhaps even more deeply nested for loop of exhaustive search. One such option would be to use the Google Cloud Machine Learning Engine. It includes a hyperparameter search tool built into it. It does better than exhaustive search. It launches things in parallel, and it does things so you don't have to do it manually. And there's a bunch of other machine learning APIs for those who are not doing or have use cases that are a little more canned. There's a bunch of APIs that are already trained. You can just send audio and get text back, send a picture and get JSON back, translate your text. So for those of you who are wondering where my animation came from and want to play around with kind of the model more, play around with training more, and you can go to playground.tensorflow.org and try out different parameters. It'll help you build a bit more intuition about what happens during training, what happens as you change various parameters of a model, and what happens as you change the data as well and the structure of a machine learning, of a neural network. So that's all in JavaScript. You can't break it. It's pretty fun. I think that's about it. So the code today is at bit.ly/keras-bbc-code. Tensorflow.org has more samples, documentation, and awesome materials. There's also a machine learning crash course that we launched a little while ago. So if you want to dive deeper, you can go check that out. It's a piece of work, but you will come out the other side feeling like a champ. So it's really quite good. And if you want to do more stuff in the cloud, you can go to cloud.google.com/machine learning. And by the looks of the people in the back of the room who want to get and take over all y'all's seats, the next session is getting started with the TensorFlow high-level API. So that's more Keras and talking more specifically about kind of how to use it and what all those pieces are. As a personal plug, I host a video series on YouTube called AI Adventures. And so there we'll talk more about things like we talked about today, various tools, et cetera. So if you enjoyed this, feel free to check that out on YouTube. We're at bit.ly/AI Adventures. All the cameras. And yeah, thank you very much for coming. And I'll turn it over to Josh, who should be somewhere around here, unless I need to stall for him. Thank you. See him.